like, yeah, so this PDF. And full screen.
Also, you should be F11, I think.
I think so.
Or maybe not. F5.
F5. Something should be. What is it? It should be like.
Do you have any clue how in Windows you can actually do the full screen presentation?
F11, no?
It was very simple.
Full screen mode. Wait. Control L.
Hey everyone, we are about to start. Please turn off the sound on your phone. Like each session I can hear the phone ringing. Please do it. And don't forget to vote in the mobile app or at the website for your favorite talk, presentation, or workshop. And please welcome Dmitry Levin.
Can you hear me? Yeah. Yeah. Okay, I'm Dmitry Levin, the maintainer of strace, and today we have a little strace session. So in the first half of an hour, I'll be talking about strace fault injection, and in the second half, my colleagues will talk about strace structured output. So, does anybody know what a strace is? Please raise your hand if you do. Okay, it's going to be fun. So, as some of you know, a strace is a traditional diagnostic, debugging, and instructional user space utility for Linux. How traditional? Well, about 25 years old, so quite traditional. It used to monitor interactions between processes and Linux kernel, which includes system calls, the most known part of it, but also signal deliveries and changes of process state. Strace has traditional command line interface, so it's easy to use, right? And it also have various filtering capabilities that make it a quite powerful tracing tool. And the last year, that's the most interesting part of it, the last year, strace has been extended to tamper with traces using so-called syscall fault injection. So today, I'm not going to focus on traditional strace features, but I'd rather talk about this new feature, which is quite untraditional for strace. But you can see some traditional output too. So what is a fault injection? It's a software testing technique used to improve test coverage of error handling code path that might otherwise rarely be followed by the means of introducing faults. Thanks to Wikipedia for this nice definition. I wouldn't be able to to produce something like this. So where do we place strace among other fault injection tools? It's obviously a software runtime tool that does it by means of syscall interpretation. It's user space, not a kernel space. It's unprivileged, and it has a traditional command line interface. So now I'll show you a series of examples so you get an idea what the interface is and what can you do with it. And I'll start with a simple program, a cat from core utils, which is dynamically linked with libc. So in the top block, you see a traditional strace output with a simple filter that shows all open syscalls. And in the bottom block, you see, well, the simplest fault injection syntax, where you tell, no, it's not going to look better this way, where you instruct a strace to fail all open syscalls. From this, you can see that the first syscall of open made by, it's a dynamic linker, by the way, it tries to open its cache, and obviously it fails. And then it tries to find libc in 4 predefined locations on this architecture, and fails, and then it gives up. Let's try to change the default error, because the default error is in a sys that is function not implemented. Let's try something different. Let's pretend that all these files are not found. So tell that error is in the end, that's no such file directory. And you can see that it makes difference for dynamic linker. When it sees this error code, it tries to find libc in 4 more locations. But it has no chance. Let's limit the number of places where we fail this open syscall to just the first one, where dynamic linker is trying to open its cache. It looks like the previous pictures, previous slides, when you've seen that when dynamic linker can't open its cache, it just iterates over predefined locations. And it finally succeeds, and everything is fine. So now let's do this. Let's fail second and all subsequent open syscalls. So when dynamic linker successfully opens its cache and reads the location where libc is supposed to be, you see it tries to open it, fails, and then it falls back to the same procedure you've seen before. It iterates over its predefined locations and expectedly fails. So you see it tries the same location, tried the first one, but it doesn't know about it because it's just different parts of code. It's just a coincidence that they are the same. This location and this location. Now let's go on and let's try to mess with open syscalls made by cat itself. So it looks like you would expect it to be. When open syscall fails, cat just reports an error and exits with error code. So this is the way how you do it. It's a bit artificial example. So you can see how you can inject faults not just a subsequent, but with a step. So this instructs a strace to inject faults starting with third open syscall, and then every second one, plus 2, you see. This way you can do some funny stuff like fail third open, and then fifth open. And you can see that cat handles this situation properly. So it opens whatever it can and processes it and reports about those that it can't open. And exit status indicates an error. Now let's combine fault injection with a path trace filter. So in the top block you see a traditional path trace filter. So you see all syscalls that have something to do with the file specified here, dev.null. And let's now fail one syscall after another and see how cat is handling this. Starting with open, but well, open we've just seen what's going to happen. So let's go to the next one. The next one here is fstart. Let's inject some plausible error. Fstart is not likely to fail, but well, what's going to happen if it does? Cat treats it as a fatal error. I don't know why. as you can see from this traditional output, it's actually not needed much, the result of fstart in this case. But, well, cat treats it as a fatal error. The next syscall, however, is an optional, because it's, as you can see, it's optimization. It instructs kernel to do sequential reading. So when it fails, like it's not available, it could be, cat just goes on. And then a read error happens, a hard read error happens. Cat also treats it as a fatal error, which is quite logical. But what will happen, what do you think will happen if, say, a temporary error will occur with read? Would cat restart or retry this syscall or not? It would. So if you inject an interrupted system call, it retries. Cat is a good program. Okay. That's the most funny thing about cat. So when it's after all this reading is done and the processing of this file is over, it tries to close it. It's a read-only descriptor. But if it fails to close this read-only descriptor, it treats it as a fatal error too. I don't know why. It doesn't sound logical. The processing is over. Oh, nice. So some more examples of fault injection syntax. Here you can specify several ones, like in the first example. And in the second example, you can see that a strace can follow descriptors and actually can see files behind them. So you can use a strace as a trivial like access control filter, which is a bit funny. Okay, now to realbox that was found with this tool. The first one is a bug in Python 3.5. Every invocation of Python requires some random data. And when it fails to either open or read data from dev.random, it generates a fatal error. But instead of, well, exiting gracefully, for some reason, it prefers to raise a sig fault at a hexadecimal address 50. Why do you think Python does this? It's just a method of an object that's not allocated. So the object is at address 0, and 50 hexadecimal is just an offset of the method. It's ridiculous. Okay, and another bug was found in libc dynamiclinker. For some omission, it doesn't check for the return code of the first mprotect call, but does for all the rest. So, and mprotect call is allowed to fail, for example, because of fragmentation. So it's a clear omission on dynamiclinker side. Why it happens? Well, just because there are different parts of code. And this was the only part in glibc the mprotect was not checked properly. So what's going under the hood? As you probably know, strace works using kernel API called ptrace. It's the same API used by GDB, for example. So when traces invokes a syscall, what happens? First, kernel puts trace into so-called syscall interstop state. This awakens a strace. It fetches syscall number and arguments from registers and memory of trace, applies its filters. You've seen a lot of them already. It may decide to print something, and then it tells the kernel to let the trace go on. The kernel is likely to execute the syscall if it's a valid syscall. And anyway, then it puts the trace into so-called syscall exit state, which also awakes a strace. It then may fetch syscall return code arguments if strace things, they could be changed. If this syscall is not filtered, a strace will print something, and then it tells the kernel to let the trace go on, and everything repeats until something stops this. So if we take all these two parts together, you can see in this strace workflow there are two places where strace could tamper with syscall numbers and arguments and return code and whatever with syscalls being invoked. So this is the way actually how syscall fault injection is implemented. Strace changes the syscall number to an invalid one, which is -1, and then kernel sees this. It's an invalid syscall, so it just returns an error code. A default one on most architectures is in a sys function not implemented, but on some it could be a different code, so you shouldn't rely on something specific on this. And then on exiting syscall, a strace just replaced this error code with the code that was specified, if something was specified. So it's quite simple, but quite powerful at the same time. As you can see from this slide, a strace could do something more than a classic fault injection, which is replacing error code. It could do some fancy stuff. For example, it could inject a signal. I don't have any ideas for real use of this, but some people do. So this is an example of how you would inject a signal right at the exiting of syscall. So you can just dump core and then do with the core whatever, like attach GDB to it. Or you can like skip syscalls, pretend that they are successfully completed, like inject or substitute an error code with a successful one, or whatever you like, and pretend that in this example that unlinked syscall succeeded and the file was removed, or I mean unlinked, but in reality it's still there, but the tracee has no idea. So this is mostly all I would like to tell about this fault injection stuff. Strace is a free software project. You can find it in many places. And now your questions, if you have some. Yeah?
When the fault injection starts on a system called entrance or exit?
So the question was when the fault injection happens on entrance or exit. It actually happens in both places. On entrance, the syscall number is replaced, and on exit, the return code is replaced. So it sits in both parts, right?
In addition to the answer, if the error code is replaced on system called exit, do you release the resources somehow? For example, it was an open call, and the file descriptor appeared actually in the process, but the error was injected.
So the question was what's going to happen with resources. When fault injection happens, no actual syscall is invoked. So it's just a natural failure of syscall. Just it's emulation of syscall failure by natural means. So if open fails, it's the application that should handle this. That's why all this thing called fault injection, that's what it's all about. You inject a real fault, not an imaginary one, and then application should handle this properly, right? Success injection is something different, and all these questions would be applicable, but this is a rather modern thing, and it's not stable. Unlike fault injection, which is part of already released strace. So, yeah, please.
Can I change syscall arguments with fault injection?
In theory, you could do this, but currently they have no interface for this. So the question was, how could we change syscall arguments with fault injection? And the answer is that technically it would be possible if we could think of some convenient interface to do this. Currently we have no interface for this, but this is likely to change in future. Yes, please.
Is this functionality available as a library as well? Is it still solely through command line arguments, or is it possible to then build other things around a library?
Well, a strace is traditionally an executable, so you probably could write a library wrapper around it, but by itself a strace is an executable. But you're the second one who asked this question, and I'm starting thinking that it might be useful. Who knows? Let's wait for a third one. Yes, please, somebody? Yeah?
Could you inject delays as well?
I know some people are hacking a strace for this, but we don't have an interface. And what kind of the question was, could we inject delays? And the answer is that it's theoretically possible, but we don't have any interface. And a delay would mean that what kind of delay? For example, when a strace traces several processes, should it delay everything, or should it delay just this process? Well, it needs some thought to make some reasonable interface. So it's not a question of implementation, it's a question of good interface. Any more questions? Yes, please? So the question is, can we specify some randomness? Originally, it was proposed to specify some randomness in this interface you've seen, but currently it's not implemented. And to be honest, I'm not sure it's a good idea, because if you're doing some fuzzing, it's probably up to a driver of this fuzzing to specify randomness. So probably strace is not a really good thing. Okay, so I don't see any more questions. The last question, yeah?
Just one about general question about the strace itself. How it affects performance, like how slow program will be executed?
Well, it's a well-known stuff. So it's a very well-known thing how a strace affects performance was the question. And the strace is a synchronous program, so everything is like synchronous. As you can see, or probably as you've seen on this workflow slide, a strace awakes several times, a lot of context switches, so it's quite a big overhead. But it's the only synchronous interface, so nothing is lost. Everything is very slow, but nothing is lost. All modern kernel interfaces are asynchronous, so you can lose some events, but it's much more fast and orders faster. So ptrace interface is just slow, but synchronous. So the last question, really last question now.
When we talk about performance, I'm curious why we already haven't dropped strace in favor of ptrace, which is asynchronous.
So the question was, why didn't we drop a strace in favor of in favor of perf, which is asynchronous? Because for some tasks we need synchronous, and we cannot allow losing any event. For different tasks, we need different tools. That's why. Right?
I don't fully agree, because the basic functionality of a strace is performed perfectly by ptrace.
The main difference, the main difference is that it's synchronous. And when you need this tool to be synchronous, you can't use perf. When you don't need, you can. That's life, I think. Okay, thank you. I think I have repeated almost all questions.
To have two speakers, so there will be two microphones. This works. Yes.
Yeah, all right.
So choose who will have.